Hello everyone, I am Akash. So I will discuss a lead code question that came this week's weekly contest. It was the second question in the contest. So the question is minimize maximum component cost. So question says you are given an undirected connected graph. The nodes are numbered from 0 to n minus 1. And the edges are given with weight to value. Uh, so you are allowed to remove any number of edges from the graph such that the resulting graph has at most k connected component. So the cost of any component is the uh, maximum edge weight in that component. If the component has no edge, its cost is zero. And so we have to return the minimum possible value of maximum cost among all components after such removal. So let's first understand the question, what actually it says. So suppose we are given a graph. 0, 2. So we are given an undirected graph. The weight of these result will be some that is given. So let's say 3, 5, 4. Let's take the exam. Okay. 6, 1, 10. So uh, our task is to calculate the means we can remove any number of edges from this graph. Our we remove edges such that ki maximum connected component should not exceed than k. The k value is given in the question. So suppose if we remove this edge, 3, still the component is 1 only. So I am assuming that k is given 3. So I will remove 3 first, but still the component count of the component is count of components is 3 if we remove 3. Component is 1, and if we remove let's say 5, if we remove 5, still the component count is 1. And if we remove now, after removing 5, if we remove 1, now the graph is divided in two parts. So the component, if we remove 1, the component count increases to 1, 2. Sorry. And again, let's say we again remove this 4. So now this part is also separated, this part is also separated, and this part is separated. So the component counts increases to 3. And now we have this as 10 and 6. If we remove 6, again one more component increases 4. And if we remove 10, component count increases 5. So maximum component in a graph can be the number of the nodes available in the graph. So we are given the n value, that is the nodes in the graph, and the node counting starts from 0 to n minus 1. So in this way, we can remove any number of the edges from this graph, and we have to, so one one condition, like one description in the question is also given that. So cost of the graph, the cost of any component. Let's say after removing 5, are uh, we have only this 0, 4, and 6. And other component is 2, 3, this weight is 10, and this weight is 4 and 6. So after removing this 5, 1, and 3, we have two components. So the cost of the components are, this component's cost is 6, and this component cost is 10. So the cost of any component is the maximum weight of any edge in the component, is the cost of that component. So here our task is to uh, decrease minimum. mm, so our task is to calculate the minimum possible value of the most maximum cost among all components after such removal. So uh, minimum possible value of maximum cost among the all components. So here the minimum possible value of maximum cost among all component is 10, and its value is 10. If we remove it this way. Second way, another way to remove the components, if we sort the edges in order of their weight, means if if we remove the edges in order of their weight. So if we remove maximum weight as first, let's say we remove 10, then we have this two component, and in this component there is no edge, so its weight cost will be 0. And in this component maximum weight is 6, weight of any is 6, so the cost of this component becomes 6. Now if we see our answer, like minimum possible maximum cost of any component, it's 6. So answer, it's 6. So the 10 is greater and 6 is lower. So it is better answer compared to this. Again, if we have, as there is a more k means more option to remove the edges, so I will remove the second largest edge, second largest edge. Like here is a 6. If we remove 6, we are we only now we have this component, and its maximum weight becomes 5. So now the result is 5. And next component, now the if after removing 6 and 10, we have still have only two components in the graph. Uh, sorry, yeah, we have only two components. This graph is actually removed. This edge is removed in first iteration only. So these are two components currently. So we have k is equals to 3. We can still remove some edges until the component value does not exceed k. So now next edge we will remove the 5. If we remove this 5, so now the component value of this component 0, this component 0, and this component value, cost of the component is 4. So now the minimum uh, maximum cost of any component is 4. So it has minimized from 10, then 4, 6, and then 5. Now it is 4. But now the component value is 3. So if we still remove any edge from this graph, we will increase the component count. That will exceed k, so we cannot move further. So it was I was removing the graph. Another way we can do is reverse of that. We start with the all components, like all edges removes, and we keep adding the minimum edge first, and until the component count becomes k, we keep adding the edges. So in this way, as soon as we get k equals to component count is equals to k, we will stop, and that will be our answer. So let me read this. Let's say we have edges. Let's consider that graph only, previous graph only. Mm, So this is the original graph say. So what I will do, I will start from all edges removed, suppose. And so all edges removed, the component count is equals to number of nodes, that is 6. So what I will do now, I will sort these edges uh, in increasing order of their weight, and I will start adding the minimum weight as first, and then greater than the minimum and so on. So until the our component, let's say I am keeping the component k value is 3. That means at max k component is possible in the graph by the constraint. So minimum is in this graph is 3. So I will add the 3. So now component count becomes 2, uh, not 2, that is 5. Component count becomes 5. Next will be 4. I will add 4. 4 with with 2, and the component count becomes 4. Next higher is either of these two. So let's say I add this 5. So in this way, we will keep checking the cost of the component also. Like we'll keep updating the result. At initial, every component's cost is 0. So at initial result is 0. And the first addition, this first edge was added. So the results become 3. In second addition, 4 was added. So the cost becomes 4. So now I will add next. Let's say I am adding this. So, but in this, after adding this, the component count is still remaining 4. Next, I will add 5. But after adding this, the result value was increased to 5. Now, but now the component count has decreased, that is equals to 3. So I have got to 3 and I don't need to add further edges because if I add further edges, it will only increase the cost of any component because the edges are sorted in increasing order. So we will terminate the uh, here and will return the return. So the data structure to be used in this question is union, find, or disjoint set because we are creating connected component of any graph. But initially, in the union find will be initialized. Union find will be initialized to all zero, all single element component like 0, 1, 2, 3, 4, 5. So all will be having only one component, one element in there. So at initially when I add this 0 and 4, one of the edge will change its representative. Like 4 can have 1 as a representative, 0 as a representative. Next I have added this 4 and 2. So fourth parent is 0 here and 2 and 4. So these parents will become 0 only. So it will have one representative element in each of one connected component. Next page, next I have added this 0 to the component. So 0 and 2, they are in same component there, so there will be no change their parents. We name this array as a parent array. And the next component I had is again 5, that is within 2 and 3. So 3 was a single component and 2 is represented index of 0. So 3 will also become the I will be added to the list of fields. So 3 is currently from 0. Now that is the key value was 3. So this was the last is to be added and the result has been updated. This result will be because the max minimum cost, maximum cost in the graph is the last edge being added because the edges are being has been sorted in increasing order. So the cost of the components will be the last edge that has been added in the graph. Means, so there is no additional calculation needed to find the cost of the components. So it ensures that the this cost value return is minimum possible value considering connected component cannot increase by k, cannot increase to k. So because we started adding with minimum edge values and until until before this final edge connected component count was greater than k. So these before smaller element edges cannot be answered. So this current edge is only answered. So that is what the explanation. Let's move to the code. The code contains the implementation of the excuse me. So I discussed we are given n as that contains the weight of the edges and k value. So if k is greater than or equal to, although will not be greater than n, uh, so k only can be there is equals to n. So whenever k is equals to n, it is equals to zero. Answer will be zero because all means connected components is equals to k. So can be can be equal to n. That will is only possible when all the edges are removed. And that is in favor of our answer also because when all edges are removed, the cost of any component will be zero. So we return zero. So there is one check I have added. If k is equals to 1, that means all the graph is connected component. And edge size is less than n. Because if edge size is equals to or greater than n, we can still remove some components from the graph to keep the components one. So in that case, we keep only first smallest n minus one components in the graph and rest greater cost is not removed in this case. But still the components remain one. Oops, one. Let me do this in the output. Mm, mm, what I was telling, let's consider this graph only. If we remove this 4, 5, if we remove 5 also, 5, we remove 5. But still the connected component is one only. So here what happened ki here was number of edges was equals to the n. And if you can also be still more edges are added, let's say 10, 12. So we can be remove them still keeping the component count to 1. But so there is no harm in removing larger weight edges to keep our result value to smaller value, some smaller value. So that's why I have considered here if its size is less than n and connected components is equals to n. Next point I have sorted the as with their cost values. And here one thing keep in mind, take these in comparative value is better by reference. So as causing time limit if I was not using this. So initially union find is initialized to n components and I keep adding one edge in the union find, so keep uniting the edge in our union find data structure and after every addition I check the component count in the union find. So if it is equals to k, I return the current edges weight as the answer. Although it will not get out of this for loop anytime, still, if all the edges are added, so the result will be the last edge weight. So let's see our union find data structure here. To keep search space smaller, generally range also means the parent contains the parent of keep the track of parent of ith node. And when a node is parent of itself, it becomes the representative of that set. And rank is kept because rank of any node is used to keep the tree as flat as possible. So at initially the component count is n and the uh, parent is initialized to itself. Parent I is equals to I and rank of each element is zero at starting. So let's we unite to two nodes. So first we find the parent of that node. And if the parent of those node is same, they are already in same component. So though there will be no need to add them, update their parents or rank. So if they are not same, if the parent of U and B are not same, we check the rank of parent of U and parent of B. If parent of U's rank is greater than parent of B, we make the parent of U to the make the parent of U parent of B also. And in opposite case, when rank of parent of U is less than parent of B, we make the parent of B parent of U also. And if they are rank are same, so in that case, we can make anyone parent of others parent, and the rank is increased of that parent. To find, we check the parent of find x in the connected component. Uh, find representative. Find the representative node in the union find. And whenever parent of x is equals to x, that is the representative of that set. Excuse me. Mm. So this was the solution of this question. Hmm. Since I returned the connected component count. So there are few things to be is this line, line 13. Actually, what it does, it keeps flattening the tree because it will reduce the uh, search space in the next iteration. Because let's show you this by example. At some point, let's say we had parent of 0 is equal to parent of 0, parent of 1 is equal to parent of 1, parent of 2 is equal to 1, parent of 3 is equal to 3. So when we start, let's say from 3, we have to check up to 0 in 3 steps. If we keep flattening the tree in that relation, we are assigning the parent of the every node in the tree is equals to parent means representative of the so tree gets flattened like this. So in next time when we have to find the parent of any node, we just only have to check one time. So they will decrease some time with some iterations. So this optimization is done in the union find work. I hope you have understood the question. If anyone did not understood, please let me know in the comment. I will try to explain as soon as possible. Thank you for watching. Hopefully you enjoyed this session. Thank you.